சார் நோ சார், அவங்களுக்கு ஒன்றும் ப்ராப்ளம் இல்லை. நான் இப்போ 3 லிங்க்லையுமே நான் இருக்கேன், நான் கன்ஃபார்ம் பண்ணிக்கிறேன். அனுஷ்டாங்க சார்.
சொல்லுங்க சார்.
நீங்கள் நம்ம லேப்டாப்பில் வந்து வீடியோ ஆஃப் பண்ணணும், ஆஃப் பண்ணிக்கலாம்.
சரி.
ஓகே ஓகே ஓகே. இப்போ பகவந்த் சார் வந்து 3 லிங்குமே ஓகே தான். இப்போ அனுஷ்டாங் சார் முதலி சார்ல வந்து நாங்கள் ரிசல்ட்
வந்துட்டாரா?
ஆமாம், நான் பிடி பண்ணியிருக்கேன். நீங்கள் அவங்களோட ஃபுல் ஸ்க்ரீன் வந்து டேப் பண்ணிவிட்டு ஓகே.
நேரம் எப்போ சொல்லணும்னு தெரியாது.
Armstrong, sir. Shall I start, sir?
Yeah, we can start. We can start, sir.
Okay, thank you. Good evening, distinguished guests, respected professors, academicians, research scholars, and students. On behalf of the Department of Computer Science and Information Technology, JP College of Engineering, I extend a warm welcome to the final day of our 5-day online faculty development program on exploring the frontiers of computation, formal language, and automata. We are honored to have you join us today. It is our pleasure to introduce our esteemed speaker, Dr.E.A. Mohamed Ali, Associate Professor of Electrical and Electronics Engineering. Today's session will delve into the topic Finite Automata and Regular Expressions, Bridging Theory and Real-World Applications. With pleasure, I introduce the distinguished chief guest of today, Dr. E.A. Mohamed Ali is a highly accomplished professional with a PhD in Information and Communication Engineering, an ME in Applied Electronics, and a BE in Electrical and Electronics Engineering. With over 23 years of teaching experience in engineering colleges, he has held positions such as assistant professor, associate professor, and head of the department, IQAC coordinator, specializing in electronics and communication engineering. He has guided numerous BE and ME projects and has involved in several funded projects, including those supported by DST and MSME, with significant contributions to rural education and socio-economic development. His research focuses on control schemes for PEM fuel cells with 23 international journal publications, 35 conference papers, and 5 patents in areas such as IoT-based systems and antenna design. He has also authored books on digital signal processing and contributed to IIP book series. He is an active member of several professional bodies, including ISTE, IETE, and IEENG, and has received numerous awards, including the First Faculty Award, Best Researcher Award, and NPTEL Elite grades in various courses. He has organized and attended numerous conferences, workshops, and FDP, demonstrating his commitment to continuous learning and professional development. Recognized for his contributions to academia and research, he continues to excel in his field, combining teaching, research, and innovation to drive impactful outcomes. May I request all participants to kindly mute your microphones during the chief guest presentation to avoid any background noise and ensure a smooth session. Thank you for your cooperation. And now, without further ado, I am pleased to hand over the session to our distinguished speaker for today, Dr. E.A. Mohamed Ali. Please join me in welcoming him, sir. Sir, the floor is yours.
Thank you, sir. Thank you, Mahesh, sir.
Thank you, sir.
Is my voice audible?
Clearly audible. You can proceed, sir. Your voice is audible.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. I am searching for how to present the slide.
Okay, sir. Okay, sir. Okay.
Sir, this is mixing. Which, sir, which option I have to choose, sir? Armstrong, sir.
Yes, sir.
Sir, present the slide. Which option I have to choose, sir?
The normal sharing
In my
option.
screen.
Yeah,
Huh?
your screen. Now share. And arrow.
Okay, you have shared, yes, sir.
Yeah, in your system.
Okay, sir. So I will display my PPT, sir. Is it?
Yeah. Whatever you are showing on your screen, that will be displayed, sir.
Okay. Is it visible, sir? My screen?
Yeah, just a minute, sir.
Sir, your video is not visible. Your slide is not visible now, sir.
Not visiting now. Just you just on the Windows Meet screen, you can see that upward direction arrow. You click that, and you can share your presentation.
Upper direction arrow.
Yeah. That will ask.
Okay, sir.
Yeah.
Okay, sir. Okay. Okay, sir. Okay, sir. Okay, sir. So, okay, sir. Okay, sir. Is it okay? Is it visible, sir?
Yes, sir.
Yes,
Yes, sir.
visible, sir.
Okay. Good evening to one and all. First of all, I would like to express my gratitude to our administrator, Reverend Sister Hamlet, our beloved principal, Dr. Rajkumar, and HOD of IT department, Mr. Sendil Murugan sir, HOD of CS department, Mr. Princely sir, and coordinators and my dear faculty members of CSE and IT department for providing an opportunity to discuss some interactive tools and practical applications regarding this theory of computation, especially finite automata and regular expression. First, I would like briefly go into this topic. Here, my aim is mainly focus on more the practical oriented explanation instead of theoretical explanation. Normally, we have studied this theory of computation theoretically. It is more mathematical. We are seeing that theory of computation with a fear. But how to understand it practically and application oriented? Let us discuss in this evening. We know that the finite automata, we know that the other name of finite automata is nothing but finite state machine. Automata is a plural form of automation. Automata is nothing but a machine, is a computing device or machine with a finite number of states. We know that what is finite is a definite size and it has a limit. Okay. Then let us understand the regular expression. Regular expression is simply here. Let us take a set of strings. Okay. So let us take a machine or computing device and set of strings. Let us understand the theory of computation concept clearly and practically. So before going to the topic, let us take a word, MS Word. Let us understand this finite automata and also the regular expression by using this word process. I take this, we have regularly using this word process. It is, I take a small word, I take a word in a word process. So here I would explain about the spell checker. So this word WORD is a regular expression. There is no error. It is acceptable because there is no indication of error in the spell checker. I change this O into U. Okay. What will happen? There is an indication of red marking, red line. Okay. So let us right click this. So this word is not in the dictionary. So the word should be WORD or WARD. This set of words are acceptable by this dictionary. So this is called as a regular language or regular expression. Okay. This machine, this computing model used to check the spelling. Okay. So this is the working of this finite automata and a regular expression. Okay, let us move to the important topic here. So before going to the topic, let us understand two theories. One is theory of computation and next one is theory of complexity. So theory of computation evolved during the period of 1930s to 1950s. Before the presence of the computer, now we are using the computer. Before that computer, the theory is evolved. The theory is predominant. Why we are going for a theory of computation? Because in older day, before 1930s, in 90s or 18th century, we are using pen and paper to solve the problem, or board and chalk that is used to solve the problem. So all the mathematician scientists wants a machine or computing model that easy the job of doing the mathematical work or mathematical calculations. So they are going for a computation theory. The computation theory is evolved for that purpose. Okay. So the computation theory is predominant in the period of 1930s to 50s, and next after 1960s, next theory is very popular, that is theory of complexity. The present day we are dealing with theory of complexity. I'm asking you, the theory of computability is very old. It's a period, it's predominant in 1930s and 50s. Why should we learn this theory of computation now? What is the purpose of learning this theory of computation? I expect your answer. You can use the chat box, or otherwise turn on your mic. Why should we learn the theory of computation? This is old one. Okay, let us understand what is theory of computation or computability theory. Theory of computation is, let us understand this theory of computation using a practical example. You can imagine you are the chef in a five-star hotel. Okay, so you are newly appointed chef in five-star hotel. You are entering into the kitchen. The supplier come with an order. Okay, you have to make the dishes according to the order. Okay, what is the first step you have to do to prepare that dish? So first, initially, we can think about the recipes available for making these dishes. So first step, recipe is nothing but a step-by-step instruction. So is it possible to make the dish or not? First step, we have to understand, is it possible to prepare the dish or not? Next, if it is possible, then we know the recipe for preparing the dish. Okay, what is the recipe? Is nothing but a step-by-step instruction. We know that the process, the procedure to cook the dish. Next, then we can check the ingredients, available ingredients to prepare that dish. Okay, this is a formal procedure if you are a chef in a five-star hotel. Okay, similarly, the computation theory of computation is dealing with the given problem is solvable or not. Can we solve the problem, the given problem? Can we solve the problem or not? Then what can computer do when the problem is given to the computer? How can that computer process the problem and arrive the solution for that given problem? This is main the theory of computation focus on these points. Next, what is the theory of complexity? Let us understand theory of complexity from this theory of computation. We'll take that same example. I am a chef. Okay, I experienced chef. Okay, so the theory of complexity is related with how fast we can cook the dish. So complexity here related with the time complexity, space complexity, and also the resource complexity. Okay, so suppose we take the time of more than 2 hours or 3 hours, what will happen? We can understand the customer will not waiting for that up to 2 or 3 hours for their food. Okay, so how fast we can prepare that dish? That is the theory of complexity. So how fast, how efficiently we use the resources, how we prepare the dish very healthy, very tasty, very with a good aroma, etc. That is very much important about the theory of complexity. So let us understand here clearly what is the difference between theory of computation and theory of complexity. Next, in theory of complexity, we have two problems. One is P problem versus NP problem. Let us understand what is P problem and NP problem. Let us understand it clearly. So, what is P problem and NP problem? What is P? That is, P is nothing but polynomial time problem. What is NP problem? NP is nothing but non-deterministic polynomial time problem. A problem takes a linear time. This is nothing but a polynomial time. Polynomial time is nothing but n square, n cube. That is called polynomial time. The problem takes an exponential time. That is called NP problem. Let us understand with our example. I take 10 minutes to cook a dish for a single person. Suppose I want to cook a dish for 2 persons. Suppose it take 20 minutes. It is a linear. This is polynomial. Suppose I take 10 minutes for cooking a food for 1 person, but 100 minutes for cooking the same food for 2 persons. What will happen? The time is in exponential. Okay. So this is called NP problem. So P problem is nothing but the solution, and the checking of that solution is very easy. Easy to solve, easy to check. That is called P problem. It's very hard to solve, but the checking of this NP problem is easy. Hard to solve and easy to check. That is called NP problem. Okay. So this is a difference between P and NP problem. Suppose if P equal to NP, what will happen? If P equal to NP, what will happen? For example, let us take a cryptography example. So we can easily the decoding of password that takes much time, even 2-3 years to solve a password. Okay, for a bank account. If the P equal to NP, this is a NP problem. It's nothing but NP problem. Okay. If decoding a password is an NP problem, suppose P equal to NP, then we can easily solve that problem. We easily decode that password. It is very dangerous for the real-time applications. Okay, let us understand this NP problem, and also this called as is further classified into NP complete and NP hard. NP complete, that means if we solve one NP problem, we can solve all the NP problems. That is called NP complete. Otherwise, this is called as NP hard. Okay. This finite automata, push-down automata, and Turing machine under the theory of computation. Okay. So theory of computation is nothing but this is a major this is a basic or fundamental for understanding the theory of complexity also. So next, let us understand what is role of theory of computation. The theory of computations play a vital role. Let us understand what is the role of. We are watching a lot of movies. What is the role of an actor? So he is a hero, or he is a comedian, or cameo, or he coming for 1 or 2 scenes, or he is in a group dancer. What is the role of TOC? TOC is like, I take the Badshah movie. The TOC is nothing but the hero, the Rajinikanth. We know that in a popular dialogue in a Badshah movie, this na oru thadava sonna nooru thadava sonna madri. So that is, we can learn this theory of computation is a basic or fundamental subject that can very useful to understand hundreds of subjects in computer science. So theory of computation is nothing but is a theory of computer science. Let us make it theory of computer science, not a theory of computer. This is make it a theory of computer science. Theory of computation is like a instruction manual. We know that we want an instruction manual for building and understanding computers and algorithms. This is used to we can clearly understand a computer and computer algorithm. This theory of computation also used to help us to solve real-time problems efficiently. Let us take three applications for search engine. We can use this theory of computation concept for quickly find the information on the internet. And the theory of computation also used in encryption. So this is used for sending a safe and secure transmission in a bank account or other transmission. This theory of computation is a base for the artificial intelligence. Now we are always talking about this AI. Okay, this is used to provide a foundation for creating algorithms that can learn and make decisions. In a research field, the theory of computation like a space research, scientists in space research. Scientists are always doing the research on the space. In olden days, they are research on moon, then Mars, then how to find a place for a human being in various planets. The research is going on. So this theory of computer science. The computer scientists study theory of computation to know which problem is solvable. So there is a problem. We know that the halting problem. Halting problem is nothing but some problem or unsolvable by computer. Okay. Then theory of computation is used for the research in quantum computing. Can we solve the problem using the quantum mechanics faster with the new technologies? And also we can use this theory of computation principle for NP and NP hard problem. For hard problem, secretly easy to solve any possible way to solve the hard problem, NP problem. This is main role of theory of computation. Then connection with the other fields. We can use this base for other fields like biology. In biology, we can the base of theory of computation is used for DNA computing, protein folding. Protein folding is nothing but the making a 3D model of the protein. It is very NP hard problem. If we find the protein folding, that will make a very big revolution in a medical field. We can solve all the disease by using this protein folding. Then in a linguistic field, we can apply this theory of computation principle for speech recognition and grammar checking also. In a physics, we can use theory of computation for quantum computing. In a cryptography, we can use theory of computation for secure banking also. Then what is the nature of theory of computation? This is a big question. Theory of computation tries to answer what does it mean to compute something. It is about understanding the essence of solving problem using rules and steps. The nature of theory of computation is about to understand what ingredients, what input you need, what steps, algorithms you follow, what disk, that is output, you end up with. There's a major role of theory of computation. This is a roadmap of theory of computation. Here, the theory of computation is a study of how problem can be solved using algorithms and machines. It helps us understand the limits of computation, what computer can and cannot do. It helps in designing efficient algorithms, programming language, and understand the capability of different computing models. It starts with a simple finite automata, then move to context-free languages, and finally to Turing machine, which are the most powerful computing model. So let us understand what is finite automata. So this automata theory, both the finite automata, push-down automata, and the Turing machines. This theory of computation deals with a computing model. This is a framework. Okay, so this is a framework with the processing unit. Is automation process. This is a processing unit with the input memory, output memory, programming memory, and some temporary memory. Now, according to the temporary memory and computing power, we can classify these automata to three. One is finite automata, then push-down automata, and Turing machine. Finite automata is nothing but the machine with no temporary memory. Machine machine with a very limited memory, very low, small computing power. So finite automata is a computing model. Let us understand the finite automata is a computing model that uses very small computing power with a limited memory, no temporary memory, but very, very, very limited memory. Let us understand this concept using a simple example. I take a small real-time application to understand this finite automata clearly. Let us take, we understand that, let us take an automatic tour. Let us take this automatic tour. Okay, I take an automatic tour. Automatic tour in various star hotels and shopping malls, etc. This automatic tour. So we have the in front of automatic tour, there is a front end pad. This is a front end pad. Then after this is a front end. After this automatic door lock, there is a back end pad. Let us understand this working principle of this automatic door. What are the states of this automatic door? Normally, this automatic door in a closed condition. When any person in this front end or back end, okay, this is a back end pad. This pad means this is a sensor. We can place a sensor here and here. Okay, when any person reaches this front end or rear end, this is a back end or a rear end. Let us take a rear end. Okay, so the sensor senses the movement of the human being and open the door. So let us understand the first. This is a finite automata is nothing but the finite state machine. So let us take this states. What are the states of this machine? There are two states. One is open and closed. There are two states, open and normally it is an open, closed state. When a person coming to front end or rear end, it should be open. Then what is the input condition? What is the input condition for this finite automata? There is a controller with automata computing model. This very, very small device is enough for this automatic opening and closing of door. We don't want any huge machine for that purpose. It's a small machine with a small memory, that is enough. So a finite automata machine can do this operation efficiently. What are the input to this to the automatic door locking machine? This is a front, any person at the front or any person in a rear side, any person at both sides. If a person entering via the front end, if he reaches this side, so the movement of the person is watched by this automatic door locker or the controller. After reaching the rear end, the door should be closed. So the both sides that should watch or neither side. This is the input of this machine. Okay. How to draw a state diagram for this machine? So we have a closed state, then open state. There is a two state. In a closed state, any person in the front side, that will be open. This is open, this is closed. This is open state. Any person in the front side, that will be open, moving from closed to open. Neither side, no one is in front or back side, that will be closed. If the person entering into the front reaches the rear side, that will be closed. And the person in the rear side entering into front side, that both side will be closed. Or there is none of the person neither on either side, that should be in a closed state. Similarly, in an open state, any person in the front side, the door should be open, maintained in an open condition. Any person in the rear side, that should be open. In a both side, that should be open. Okay, this is the state diagram to represent this example. So similarly, we can draw a state transition table. Okay, let us take two state. One is closed state, another one is open state. So let us take the state here and input here. Let us take the input. We have four inputs. One is neither side, front side, rear side, or both side. If normally closed condition, neither side, that means that should in a closed condition. Open side, neither. Okay, let us take neither in a closed state. This is in the neither condition, that should be also a closed state. In an open state, there is a neither, that means that should be in a closed state. Then closed state, the person in a front portion, that should be open. In an open state, a person in a front side, that should be also open. The closed state, any person at the rear side, it should be closed. Moving to the rear side from the front side to reaching the rear side, that should be closed. Rear side, that should be closed. Then any person in a rear side, that should be open. Entering into this rear side, it should be open. If it is open, entering into rear side, it should be open. Input. The both side, if it is in closed condition, the both side, that will be both side, that will be in a closed condition, that should be in also maintained in a closed condition. The both side, if it is in open condition, open state, both side, if two persons are entering into both side, that is also maintained in the open condition. Okay, so we can understand this state diagram and state transition table to understand the working of this finite state machine. Okay, what is this? A finite state machine means that is a very limited machine with a very limited memory. Then the push-down automata is nothing but it's a improved version of finite state machine. Here we have a stacked memory. Okay, so with the minimum computing power, it's the next computing model. So this is used for mainly for programming, checking the programming language or mathematical expression. So nested structure, etc. Then the Turing machine is nothing but just like a computer with a today we are using a computer. This nothing but a computer. This highest computing power with a very huge memory, that is called Turing machine. So finite automata is a small machine with no limited memory and low computing power. Push-down automata is nothing but next medium level machine, so moderate computing power and a small stack memory. The Turing machine is nothing but is had a huge memory and access memory and highest computing power. Okay, so let us understand this algorithm. Algorithm is nothing but you can start with a problem, for example a sorting problem. So you follow the set of instructions, that is nothing but algorithms. So in a sorting problem, let us compare the numbers and according to the number, let us arrange the number in ascending order. So take two numbers, then check the number, and according to them, swap that number. And then finally, after completing all the process, all the numbers, you get a solution. It's a sorted list of numbers. In algorithms, the finite automata, the real-time application of finite automata is we can use this finite automata for spell checker or traffic light controller, etc. The context-free next level is push-down automata or context-free grammar. This is used for programming language compiler. This is used for checking nested structure. In a programming language, suppose I want to explain with an example. Let us write this push-down automata is used to check the syntax of any program. I take a small program, small for loop. If it is visible, sir, my screen is visible.
Yes, sir, it is visible.
Sir, visible, but small letters. Kindly zoom it.
Okay, sir. Okay, sir. Okay, let us take a for loop for I in range 10. Okay, print TOC. The program just print TOC 10 times. Okay, suppose I miss any line, any command in this for I in range 10, I miss a bracket or I miss a colon, that indicate there's a syntax error, expected colon. Okay, this is done by the program, the syntax is checked by this push-down automata. Suppose you can check also, I take I in range 10, I miss a bracket. By I put a colon, I miss a bracket. There is a syntax error. Okay, so these nested brackets is checked by the push-down automata. Okay, let us understand this concept, this language, grammar, and machine problem algorithm clearly. Let us understand what is finite automata and also regular expression. Then I slowly moving into grammar. I take a regular expression AC. I take a regular expression AC. It's a string with the alphabet A and C. So let us realize in a finite automata, this machine, these two word AC. So let us start with a start state. I take it's a start state. Then it reads a first character, first alphabet A. So it reads the character A. Then it reaches to second state. So second state. Then it reads the second character C. It moves to the final state. Okay. So this is a finite automata. This is equivalent to this regular expression. This is used to accept this regular expression. I change this regular expression to A, B, C. How to draw a finite automata for this letter A, B, C? So A, here we have A and C. So let us take a B here. I take a B here. So this is A, B. But this B is not a single B. We can repeat this again and again. Okay. So let us take this is A, B, 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 etc. C. So this occurrence of B is 0 time. It may be occurrence in a 0 time or more times. Okay, it may be a AC or ABC or ABBC or ABBC. Okay, let us mark this occurrence of 0 or 1 by replaced by the symbol star. Star is nothing but a quantifier. So this is occurrence 0 or more occurrence, that is represented by the symbol star.
Sir, what did you just say? Is it a quantifier or modifier?
Ma'am?
Star is what? That closure is what? It's a quantifier.
Yes, sir. It says, ma'am.
Okay. Right.
Okay. So let us take A, B star, C. How to arrange the grammar from this is a equivalent of this finite automata is equivalent to this regular expression. How to arrive the grammar for this A, B, C, this regular expression? Let us take a Chomsky type 3 step. Type 3. We can arrange this grammar in a 3 steps. So let us take the sentence S. Okay. This start with A. Let us take ABC or A, B star C. ABC. The first word is A. First alphabet is A. Then I take a B. Okay. So then this is A. The remaining letter is taken as B. So next B tends to. Let us make this P into B. Next letter is B. B. So B. Then we make B to C. Okay. So this A, B, C is written in a grammar. Yes, sentence A, big B, B, and B is replaced by small b and then B. So first BC, then C. Okay. We can combine these two. Okay. Here B or C, either B or C. Okay. So let us take first step is, we can maintain first step as it is A, B. Then second step and third step, or we can combine these both. B tends to BB or C. This is the grammar. So both are the same. The finite automata and regular expression and the grammar both are same. So we can understand this. I would explain about the automata language. Language and regular expression. Okay, let us understand what is automata, language, and regular expression. I take an automata, the start and end of the state is same. The state is taken as a start and also end state. In a language, there is no movement, no transition. So this is the empty state, epsilon. It is represented by the regular expression is represented by epsilon. Suppose I take it is a start state. It is a start state. Then it reads A. It moves to the final state. It's a final state. This is represented by the letter A. Language, in a language, let us represent it is a A. In a regular expression, it is A. I start here and it reads alphabet A and it reaches the final state, and also if it reads another one alphabet B, it also reaches a final state. We can both two alphabets. So in a language we have A and B. In a regular expression, this is represented by either A or B. So it is represented by A plus B or A or B, either A or B. Similarly, let us take a start state here. It reads A and it reaches to next state and it reads B, and after that it reaches the final stage. We can two alphabet here. So the language, in language we can represent A comma B. In the regular expression, it reaches A concatenate with B, A multiplied with B, A concatenate with B, or let us write this as AB. In short, we can write AB. Is it clear? Okay. Is it clear?
Yes, sir.
Okay. Next, I take in a finite automata, I take is a start state. It reads A then it reaches, sorry, the start state. Also, a final state, it reads alphabet A. What it means?
Sir, it's
What
A
it means?
closure.
A closer. So let us take this in a language. This is, it may be a empty set or A or AA or A, etc. So in a regular expression, this is represented by A star. So occurrence of A 0 time or as many as time. Okay, 0 or more occurrence. This is represented by A star. And similarly, let us take, start from a state and it reads A and it reaches a final state. This is a closer in the final state. We say also A. How can we represent this? It reads A and A again and again. So let us take A, etc. So it is nothing but A plus. This is nothing but A star. Okay. So similarly, we can represent a lot of things. So I stop this here. Okay. So I would like to give a practical example and then move to JF lab. Okay. So I would like to explain another 10 minutes. So practical tools JF lab. Let us take a JF lab. I take a machine. This is a finite automata machine. Here we have a 3 state, Q1, Q2, Q3. Okay. If it reads 0, it repeated here Q1. If it reads 1, it moves to Q2. If it reads 0, it moves to Q2. In this state from Q2, suppose it reads 1, it reaches the final state Q3. If in a Q3 it reads 0 or 1, it is a closed state. It's maintained in a final state. Okay. So if the input is 0, 1, 1, 0, 1, what will happen? If it is 0, 1, 1, 0, 1, so let us take here, I take 0. 0 means Q1. Let us start from Q1. If it is 0, this is in a Q1. Then next input is 1. If it is 1, this move to, sorry, if it is 0, it is in a Q0. If it is 1, it is moved to Q1. Next, if it is 1, it is moved to Q2. Then if it is 0 or 1, it is maintained in Q2, final state. 0 or 1, it is in final state. So it is accepted. Suppose the second case, I take 0, 0, 1, 0, 1. Let us take, if it is Q1, then I give an input 0. Okay. If it is in 0, Q0, it is 0. If it is in Q1. Sorry, it's a Q1, sorry. Q1, this is Q2, this is Q3, sorry. Yeah. Right. The second, let us take this state 0, 0, 1, 0, 1. So start with Q1. If it is 0, then it is in Q1. Then if it is 0, it is also in Q1. Then if it is 1, this move to Q2. Then if it is 0, then it is returned back to Q1. Then if it is 1, then it is finally returned to Q2. So it can't reach the final state. So this is rejected. So let us practically, I would like to realize this using this JF lab. What is the JF lab? What is the expansion of JF lab? JF lab.
Sir, no idea.
JF lab, let us so AP means automata package. This is automata package. JF is Java formal language. Okay. It is developed by developed by Susan Roger in the year 1990. He is continuously teaching this theory of computation subject. He has to prepare a programming model to check the assignment of the students. So if it is correct or not. So he started that work to develop a program to check the assignment problem given to the students. So let us if it is visible, this screen is visible. Here we have in JF lab, here finite automata, mealy machine, more machine, push-down automata, during machine, etc. So, okay, let us take a finite automata. So let us solve, let us make this single problem. I explain this problem, one or two problems using this finite automata. So first here we have a attribute editor. This is the attribute editor. Next one is state creator. Next one is transition creator. Next one is deleter. So let us take first, let us create a state. I click here, state creator. Okay, then click the button here. So Q0, we want three stated, Q0, Q1, and Q2. Okay, so I take three state. So I assign here, I take the attribute editor, I take the attribute editor, I assign Q0 is the initial state and Q2 is final stage. This is the final state. So next I take the transition, I take this transition. So I mark this here, Q0, I enter Q0 value is 0, enter that. So this is Q0. Then the input reads the next transition here, Q0 to Q1. The alphabet here is 1. Next, Q1 to Q0, moves Q1 to Q0. This is 0. Okay. So next Q1 to Q2 to Q1, the transition of Q1 to Q2, with the input of 1. Then Q2 to Q2, the closer, the final state, the transition of 0 and the transition of 1. Okay, I have created, if it is it clear? Is it visible? Do you understand this?
Yes, sir, it is.
Yes, sir. Yes, sir.
Yes, sir. Okay, so I give a input. I want to check. We can check this by state, step by step, or fast run or multiple run. Okay, suppose I want to give a fast run. Suppose I want to take a fast run. I give an input 0, 1, 1, 0, 1. So the final state here. So I enter 0, 1, 1, 0, 1. This is accepted. Okay. Suppose we want to give a multiple run. I give a multiple run here. Enter 1, 0, 0 or otherwise 0, 1, 1, 1, 0, 0, 1, 0, 0, 1. Etc. Okay. So here we can run the input. So this 0, 1, 1, 0, 1 is accepted, but 0, 0, 1, 0, 0 is rejected. Okay. We can give a lot of input and check the result here. Suppose we want to check step by step, we can give the input. Suppose I want to check 1, give 1, sorry, 0, 1, 1, 0, 1. Then we can check the step by step. We can check next 0, next step is 1. Okay, so there is a color change in the next state, Q1. Next state is Q2. Next it reaches the final state. Okay, it reaches the final state. Suppose I want to give a other input. Zero 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 101. Suppose I want to give the input. So we can check step by step. 0, the state is Q0, then 0, it is in Q0, then 1, it is in Q1, then 0, it is returned to Q0, then 1, it is returned to Q1. It's not accepted state. We can check, right click, and we can trace the output also. Okay. Is it okay? So I give one or two tools about to check the regular expression. Suppose I enter A. I convert this A into non-finite automata. This is a non-finite automata. Suppose I want to enter an expression A plus P star. So let us convert this into non-finite automata. This is a non-finite automata. So then do steps. This is an entire non-finite automata. Then we can convert this into, we can see this clearly. By using a layout graph. This is the entire layout of this regular expression in finite automata. சார் இன்னும் ஒரே ஒரு டூல் மட்டும் சொல்லி முடிச்சுக்கலாமா இல்ல முடிச்சுக்கலாமா சார்? டைம் ஆயிடுச்சுன்னு நினைக்கிறேன்.
Sir, can you show it again?
Ma'am?
Can you show that again?
Yes, ma'am.
The last diagram that you
I enter a regular expression A plus B star. Suppose I want to generate an NFA, non-deterministic finite automata, for this regular expression A plus B star. Okay. Then go to convert to NFA. Convert to NFA. This is NFA. Okay. Do steps. Slowly click these 2 steps and then select this cursor and right click and select layout graph. This is the layout of this NFA for the regular expression.
This is NFA or X. Okay.
NFA for regular expression A plus B star.
Yes, sir. Got it.
Okay. Similarly, you can give a regular grammar also. We can enter the grammar also here using this JF lab. Sir, Sindhulkumar sir. Sir, ஒரே ஒரு டூல் மட்டும் சொல்லி முடிச்சுக்கலாமா இல்ல முடிச்சுக்கலாமா?
ஓகே சார், ஓகே சார், கண்டினியூ.
ஒரே ஒரு டூல் மட்டும் நான் சொல்லிறேன் சார்.
No problem, sir. You can take it.
ஓகே சார். ஒரே ஒரு நிறைய டூல் இருக்கு சார், நான் ஸ்லைட்ல போட்டிருக்கேன். பட் நமக்கு டைம் முடிஞ்சதுனால நீங்க என்ன பண்ணலாம், இந்த இதுல let us take out debugx.com. நீங்க இதுல ட்ரை பண்ணலாம், நீங்க மொபைல்ல ட்ரை பண்ணலாம், அல்லது உங்களுக்கு லேப்டாப்போ கம்ப்யூட்டர்ல இருந்தா கூட நீங்க debugx எழுதிரவா இதுல debug DEBU நிறைய டூல்ஸ் இருக்கு. நான் ஒண்ணு மட்டும் சொல்லி முடிச்சுக்கலாம்னு நினைக்கிறேன். debugx.com.
I'm sorry to say, but we don't understand Tamil, so if you can please tell us in English.
Okay, ma'am.
Thank you.
So take a debugx.com website. debugx.com.
Participants, I thank you for your active participation and regular attendance. Your engagement and enthusiasm have made this program.
Okay, let us go for this.
Special thanks.
I take this debugx.com. Okay, Is it visible?
The Department of Computer Science
Yes, sir.
and
Okay, I take the Python. Python is comfortable for me. So I take the language Python. Here, Python.
I'd like to express my special
So I enter a word. Here I take a text A, B, C, suppose. Here I give these are regular expressions I given to the finite automata. This is a start state, this is a end state. Let us check the
forward to
word ABC that give a matches. Suppose I enter here A, X, C, it doesn't match. Suppose I want to check a email. Suppose I want to check a email. Let us enter the email as like a first. Let us take a caret symbol. Caret symbol. If is it visible? Sorry, is it visible?
Yes, sir.
Okay, sir. Now visible, sir.
First enter the caret symbol, then the bracket, then I take, so first I take A to Z. The first, suppose this username at domain.com. Suppose I enter the username domain.com, A to Z, and also capital letter A to capital A to Z, and text also given in a domain, the mail ID. So 0 to 9, and there's some special character, underscore, plus, etc. We can give that. Then add, plus, add symbol. Next location is add symbol. Then I take the same A to Z at gmail.com, at yahoo.com, etc. A to Z, capital A to Z, 0 to 9. Okay. So then plus .com / dot, then it may be a .com or .net or .org. So let us com or net or org. Org plus the finally end with a dollar symbol. Is it okay? Okay, I take A to Z. Okay, then capital A to Z, 0 to 9, underscore, plus symbol. Okay, here at, this is start with the caret symbol, at some text A to Z, capital A to Z, 0 to 9, dot. It may be a com or net or org. Okay, let us check a mail ID if it is correct or not. Okay, I take here. Suppose I take user at domain.com. It matches. Suppose I change this to user at, it doesn't match. Okay, do you understand this?
Yes.
How to check a mail ID using this finite automata machine and also the regular expression. How to give a input and how to check this. This entire process is done by / 2 letters. That is / I replace this and open it. / small w. That means all 0 to A to Z, 0 to 9, all included in / small w, and / capital W that include all the special characters. Okay, I take this plus the final state is the dollar symbol. Okay, so I take / W small case, / W capital, then this / W, that means A to Z in lowercase and uppercase and all the digits 0 to 9, etc. So let us understand this using this sheet. Here this is a caret symbol, this is the beginning of string. The dollar symbol is the end of the string. Okay, / D is a digit. / W is a word character. / capital W is a non-word character. Let's enter this. Okay. Is it okay? Is it clear? Similarly, we can use another these regular expression tools to understand the concept, one is regex 101. Regex 101. Another one is regwix.org. So for regex 101, we can check this also. I take the caret symbol, backslash W, backslash capital W, plus the end is dollar symbol. Okay, I check whether a username at domain.com is a mail ID. It matches. Suppose I give a 2 dot, it also matches because I give a entire. Suppose I want to give a specified character. Let us change it into A to Z. That type of. Let us give a list of alphabet like A to Z, 0 to 9, etc. Similarly, we can use regwix is another tool. So we can use this tool also to understand the regular expression and finite automata. Okay. So there is a match. There's a lot of tools are available to understand this theory of computation and finite automata, etc. So I would like to stop here. I take much time, excess time. So sorry to say. Thank you so much for watching this session patiently.
Not a problem.
Okay, if
This
you
is the first
can
time
ask
I
a
have seen
question. Okay, ma'am. Can you ask any question regarding this today's topic?
Sir, is there any tutorial available that we can go with the JF lab?
Okay, manual is available in the jflab.org. You can download that manual.
Okay, and is that a freeware? I mean, so free open source.
Yes, freeware. We can download it.
All right, all right. Sir, one thing more I want to ask, like if we are working on some genome data, analysis of genome data, will that also fall in the category of NP hard problem?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Right. Thank you.
Thank you so much.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
We hope that today's session led by Dr.E.A. Mohamed Ali has provided you with a deeper understanding of finite automata and regular expressions, bridging theory and real-world applications. We kindly request your oral feedback on our 5-day online faculty development program. Your input will greatly help us improve our standards for future events. Please, I request all the participants turn on your video, then give your feedback, ma'am. Please.
Hello, sir. Sir, can you hear me?
It's audible, sir.
Sir, I am Vivekanandan speaking from St. Joseph University, Sumakudima, Nagaland.
Welcome, sir. Please share your experience, sir.
Sir, this kind of FDP program is rarely used for all the staff members to improve their knowledge. Apart from knowledge, we are recalling the subject which we are not taking it. Moreover, the resource person's presentation is very good, sir. Sir, organizing this kind of online program for faculty is very important nowadays, sir, because all are working in a college and doing our duties sincerely and efficiently. This online program really helps us to remember and develop our knowledge, sir. Thank you, sir.
Thank you so much, sir. Thank you so much for your valuable insights. Thank you, sir.
Thank you, sir.
Next, anybody? The participants share your experience, please.
Sir, may I say something?
Yes, ma'am. Please, ma'am.
Actually, this kind of FDP and TOC, I don't think that happened earlier because we attend some FDPs on, let's say, quantum computing or Gen AI on machine learning or something kind of it. But this is the theory of computation. FDP has been conducted for the first time in my experience, and it was really good. So I would like to request you to, if you have some more expert, we can also arrange some more FDPs. So we would like to attend that also. And for today's session, it was really very informative. The resource person was very, clear and. I mean, this is the first time I have seen the JF lab that theory of computation can also be implemented on a software also. So thank you so much for connecting us with a pool of experts, and that's it.
Thank you so much, ma'am. Thanks for your valuable feedback, ma'am. Thank you. Okay, a general announcement. To receive your FTP certificate, please complete the feedback form available today. As part of the form, kindly upload your photo within 10 MB. Upon submitting the feedback form, your FTP e-certificate will be generated automatically.
Sir, I submitted my photographs yesterday successfully. So do we need to do it again?
We will check out, then we will reply to you, ma'am, individually.
Okay, right. Fine, I'll do. Thank you.
Then you can receive your certificates in your registered email. Also check in spam of email. We request all participants to fill out the feedback form carefully and completely. Your input is valuable to us. Don't receive your certificate after submitting the feedback form. If you encounter any issues, please reach out to us through our FTP WhatsApp group. We will be happy to assist you and resolve the issue promptly. Then now it's time for us to bid farewell to our highly successful faculty development program. As we conclude this 5-day event, I would like to express my heartfelt gratitude to everyone who made this program possible. First and foremost, I would like to thank our esteemed administrator, Reverend Sister Hamlet, and our respected principal, Dr. Rajkumar, for their invaluable guidance and support in organizing this FTP. I would also like to extend my sincere thanks to all the resource persons who generously shared their expertise and time with us. Your contributions have enriched our knowledge and understanding of the subject matter. To all the participants, I thank you for your active participation and regular attendance. Your engagement and enthusiasm have made this program a truly rewarding experience. Special thanks are due to Mr. Brinsley, Head of the Department of Computer Science, and Mr. Sendil Murugan, Head of the Department of IT, for their tireless efforts in organizing this FTP. Last but not least, I would like to express my special gratitude to Dr. Armstrong, Associate Professor, Department of Computer Science, for his invaluable support and contributions to the success of this program. Thank you all once again for making this FTP a memorable and enriching experience. We look forward to continued support and collaboration in our future endeavors. Thank you all.
Thank you, sir. Thank you so much for the organizing committee.
Thank you, ma'am.
Thank you, sir.